Good afternoon. This is David Eastwood, Geotech Engineering and Testing. Um, Today, we're here about this geoforensic evaluation of a metal building in Houston. I hope everybody can hear me. Um, if you can't, shoot me a chat, some email, something, um, Q&A or chat. Send me you cannot hear me. Um, Project background. Before we get to that, of course, I want to talk about the audience. We have about 190 people are RSVP'd, and most of them are engineers and building contractors that have attended. I work for a company called Geotech Engineering and Testing. The firm has been around for about 39 years. We do geotechnical, environmental, materials, and geoforensic engineering work. We look at a lot of failures, building foundations, slopes, retaining walls, general anything soil structure interaction involved. We get involved in that. We got about 65 people, and we work all over Texas, Louisiana, New Mexico, Oklahoma, Arkansas, and really we work all over the United States. So just giving you a little background on us. Let's talk about project background here. Here's the building. This is a big metal building that's located north of Houston. And what happened was there was a dispute between the owner and the contractor. So the contractor left the project site in the middle of the construction. So they did the framing, put some metal sheets on the building, and then they left. And the owner hired us to try to figure out what's the existing condition of the building. And so we were hired to go out and figure out what's wrong with this building. Here's some pictures of the building. The drainage around the whole building was horrible. It was like a lake, poor drainage. So we did, of course, site visits. We did field exploration, laboratory testing, engineering analysis, figure out what's wrong with the foundation system, what's wrong with the building, and what kind of repairs they need to do, what kind of additional studies they have to do. Timeline. They did a soil test for the building in 2021 in August. March of 23, they got the structural drawings done. The civil drawings were done in 24 May. The contractor, the owner, kind of split. They hired us in January of 30th of 2025 to go look at this thing and figure out what's the existing condition of the building. When we went out there to look at it, we saw a lot of problems on the floor slabs, but here's some of the problem areas here and here on the building. This is north, and so a lot of stuff in the south side of the building. These observation points 1, 2, 3, 4, 5. Interior of the building. If you go out there and look at inside the building, you see a lot of building materials stacked up over there. Put a lot of pressure on the floor slabs, and a lot of shrinkage cracks. Looking at the floor slabs all over the place, there were a lot of shrinkage cracks. And joint separation, controlled joint separation, construction joint separations, almost as much as half an inch to an inch in some areas. So these are the joint separations. A lot of cracking at the edge of the joints. Poor quality concrete. You can see the joint over here. Water was coming out through the joints. The soils were sandy in this area underneath the slab. They had some areas where you have sandy clay, but since there was water standing everywhere and the whole ground was really wet, water was coming through the slab, and you can see that the slab area is all moist and dark in here. And you can see the joints, kind of joints filled with water here in the floor slabs. Looking at the anchor bolts, this is how they were looking at. They were putting anchor bolts inside the joints, which is totally messed up. And some of the washers were missing, and some of the bolts were missing. It was just a very sloppy work. I guess this guy left and just left the whole thing the way it is. And you can see the anchor bolts. Some of them were missing. These are on the columns. You can see here some of the other anchor bolts in the building that were missing. The bolts, the washers. Pretty rusty stuff there. The real sloppy construction. We noticed inside the building they had forklifts running around. So they were lifting this construction materials, stuff that they have, and they were using forklifts to move it around. So that's one of the things we looked at to see what's the effect of these forklifts on the floor slabs, the loading and all that. The exterior of the building, it was a lake, real poor drainage. They haven't really graded it outside very well. I guess the contractor left before the proper grading was done, and water was standing around the building. The foundation system for the building consists of the floor slab. The floor slab was a 6-inch concrete floor slabs with number 4 bars at 12-inch spacing. You can see you have grade beams in here, spread footings, grade beams here, spread footings. There are different types of spread footings on this thing here. For number 1, the concrete on the slab was supposed to be 3,500 psi. The spread footings were 6 foot by 6 foot by 1.5 feet at elevation -5, 6 by 6 times 1.5 elevation -2. So the spread footings were at different elevations. I'm not sure why. Typically, I like to put them all the same depth, but these are the different depths. And there were reinforcements, cover, about 3-inch cover on the reinforcements. And there were, they had number 6 bars at 10.8-inch intervals, kind of like, I would just call it 11-inch or, 10-inch. So anyway, funny numbers. Here's a typical grade beam, section is about 14 inches wide, 36 inches deep. Going out here, this is the slab. It's supposed to be sand under the slab, leveling sand at 4 inches. The subgrade should be compacted. Here's the typical makeup spread footings, but in this case, 36-inch plus 15 inches deep. So that's 51 inches deep. That's the concrete. You can see that spread footings. Here's another spread footing that's supposed to be about 5.5 plus 15 inches deep. It's a bigger spread footing. These are the construction joints. They're supposed to have dowels. And then for the control joints, kind of a crazy, they put it on the drawings. It says, provide control joints as a slab that no distance is greater than 40 feet, and square footage is less than 1,600 square feet, which is in the 40 feet is crazy. Typically for 6-inch concrete floor slabs, I would go with 15-foot joint spacing. Really, maybe 12 foot, 12 to 15-foot control joint spacing, not 40 foot. So that's not good. Although when we were at the job site, they didn't follow that. They had the control joints at about 15 feet. Yeah, he says the control joint should be about 15 feet apart. Field exploration with the GPR, ground penetrating radar, concrete coring, drilling, piezometer installation, micro elevations, test pit excavations, bolt testing. This is the floor slab areas. C1, C2, C3, these are where we did concrete coring, and we did 10 cores to evaluate the concrete composition and thickness. And then we did borings. We did also micro elevations. In terms of field exploration, we did 6 borings. In the in 6 borings, 25 feet. So 6 of the borings were 15 feet interior, and 6 of them outside, 25 foot deep. We put in two piezometers in the borings, piezometer P1 and P2, to see what kind of a water level we have underneath the floor slabs. We did test pits, total of 8, 4 locations near the spread footings, and these are the test pit location: test pit 2, test pit 6, test pit 3, test pit 1, test pit 5, test pit 4. These are test pit locations. Test pit 7, to evaluate the size of the spread footings and the grade beams. Also, we did bolt testing to see if the bolts were tight enough. So we check on the torsion and on the torque on the bolts to see if they were tight enough. So we did borings, 6 of them inside, 6 of them outside, put 2 piezometers in, and we did 8 test pits, 4 at the spread footings and 4 at the grade beams. The GPR basically is a device that uses an antenna that transmits electromagnetic energy similar to cell phones. A receiver picks it up and got a reflected signal. From that, it defines the if there's moisture underneath the floor slab, there are voids underneath it. So that's what it looks like. It's used really a lot in forensic engineering. You just run it on the floor slab areas. We picked up 10 locations where we did coring to make sure we're not going to core in the steel area. So GPR picked up the locations of the steel, and we used 10 locations to evaluate the spread footing locations with GPR. Also, we ran the GPR to see if there's areas of voids and high moisture in the floor slabs. Here's the GPR we're running it. This is what it shows where the steel is. The drawing the lines is where the steel is. So we did the core over here, for example. These are the steel locations. That'll be number 4 bars. So we just run it at different locations. Again, we picked up the boring. These are the steel locations. That's C3, core number 3 here. And the steel is over here. C number 4, core number 4. These are the steel locations. This is core number 5. Also boring number 1. The steel locations. That's C6. It's the boring locations. B2, concrete core number 6. Steel locations. That's number 7. We did the core over here. Those are the steel locations. That's boring B3. Uh, Here's number 8, boring B4. This is uh, core number 8 and boring number 4, steel locations. They had already saw cut the slab in this area. So we use this to calibrate the GPR in terms of the thickness of the concrete and all that. That's the boring B5 area. We put it over here outside the steel area. This is the C10 boring B6. And we picked up this location right here outside where the steel is to do the borings. These are the rebars. And then we run the GPR throughout the whole slab areas. Of course, you see areas of high moisture. And as you can see, there's a lot of water just sitting on the slab because the roof was not completed in some areas. So it would just rain right on top of the uh, floor slabs. It's the GPR pictures here. Concrete coring, we cored the concrete at multiple locations, at 10 locations in the floor slab areas to see what kind of concrete we have. So to determine the concrete thickness, petrographic analysis of the concrete. Here's the thickness of core number 1, 6 inches. Core number 2, about 6 inches. Core number 3, about 7 inches. Core number 4, about 5.5 inches. Core number 5, about 5.5 inches. Core number 6, about 7 inches. Core number 7, about 5 inches. Core number 8, about 5 inches. Core number 9, about 6 inches. And core number 10, about 5.5 inches thick. At core number 1, when we cored it, there was kind of like a void underneath the slab. So it was like a half an inch or so void under the floor slabs. Interior borings, we went out there, used our portable rig to do borings out here. We did some borings 15 feet deep, sample at 1 foot intervals, and we got samples of the soil, see what the compaction is or what kind of a soil we're going to get. We also use our truck mounted rig to do borings out there. We have like 10 drill rigs, so we can get out projects quickly with our rigs. These are all our own rigs, and we drill the holes at various locations. It's B6. These are some of the samples of sandy clay material, CL, lean clay type material coming out. We measure the water level in the holes that we drilled 15 feet deep, and we couldn't find any water. After we finished the drilling, we grout the holes with a mixture of bentonite and cement. I made a grout and fill the holes with grout from bottom up. So that's what the top of the grout looks like. 2 of the boring locations we turned into piezometers, but didn't grout those. Exterior boring, we used our buggy rig system. The ground was so soft we couldn't use the truck rig, so we used our own buggies and got soil samples to see what we got over there. We went down 25 feet deep with our buggies. Piezometer installation. 2 of the boreholes we did for soil sampling, we turned them into piezometers. Piezometer 1, piezometer 2, to figure out if there's water under the slab. It's basically you got a 5-foot screening here, right there, and then you got sand around it, and then above that you got bentonite to seal the thing so that you don't get surface water coming into the hole. So you got a PVC pipe. It's about 2 inches in diameter, and in this case, the screen length was 10 foot. Total piezometer depth was 15 foot. So we had 10 foot of screen here to see if there's water coming in. It's these 2-inch diameters PVC pipe. That's the piezometer installation when we drill the holes, put the PVC pipe in there. That's the screening here, 10 foot screening it. Put it in there, put sand around it. And then the top 5 feet, put bentonite balls. This bentonite expands as soon as it gets wet and seals and doesn't let the water from the surface to get inside the hole. So what we're measuring over there is the groundwater and not surface water. It's a typical piezometer cap. We measure the water level in the piezometers. 2 piezometers we had, and piezometer 1, piezometer 2, and they were dry. There was no water in them. No groundwater. Micro elevations. We want to know what the elevations of the surface was of the floor slab and compare it to the allowable deflection that's in the F.PTI, Foundation Performance Association elevation document. So we use the basically Stanley tool device here and measure the elevations throughout the whole floor slab and figure out what the elevations are everywhere, what we call relative elevations. That's the contour we got of the elevations. The dark green area is the areas that are higher in elevation, and the white areas are the one on low in elevation. So roughly you can have from -2 to +1, almost 3 inches elevation change. I think we found somewhere about 2 inches of elevation difference throughout the whole slab area. Test pit excavations. We want to know test excavation here. We want to know what the size of the grade beams and the size of the spread footings are actually out there. So we have what kind of soils we have underneath them, well, how strong some of those soils are, if there's any water underneath near the foundations on the spread footings. So we excavated the foundation systems. We got shovels and started excavating. Trying to expose the spread footings. You can see the spread footing in here. That's test pit number 1. The width of the spread footing. Trying to figure out what's the depth below the top of the grade beams. It's a test pit number 2. Excavated. Trying to get the width, depth on them. Test pit number 3. Get the width, the depth, the soil conditions. It's 18 inches thick. Test pit 3. This is test pit number 4. And you can see the spread footing width, the thickness, about 18 inches. And the depth below grade, 51 inches below grade. Check with the hand penetrometer to see how the clays were, sandy clays underneath the floor slabs, underneath the foundations were, getting measurements. The hand penetrometer testing. For grade beams, we excavated to try and check out the grade beams to see how deep they are, how wide they are, and what kind of soils we have at the bottom of the grade beams. So we excavated the grade beams. You can see the width. So the excavation is trying to measure the depth. Oh, well, there's a various measurements trying to measure the width. Test bit length in this case was 32 inches. 30 inches, test bit number 6, the width was. Test bit excavation width. Test bit number 7, measuring the depth of it, 36 inches, beam depth. Measuring the beam width of 14 inches, that's the design. It's supposed to be 36 by 14. Test bit depth was 36 inch. Test bit number 8, beam depth was 34 inches, supposed to be in 36 inches. The beam width is 14 inches, which is design says 14 inches. These are the excavation sizes. That's the depth. We excavated 42 inches. As soon as we finished measuring the size of the foundations, we backfill the areas in lifts, put the soil back in, use a jumper jack to compact that soil. Make sure it's nice and compact. So, what it looks like. So in summary, test bit number 1, from 0 to 62 inches, we had lean clay, which is sandy clay. Spread footing was 15 inches of thickness. Design was 18 inches thickness. Spread footing width 72 inches. Design was 72 inches. Spread footing depth below slab 81 inches. Design was 84 inches. There was no water at the excavation. Test bit number 2, from 0 to 42 inches, we had lean sandy clay. Spread footing thickness was 20 inches. Design was 18 inches. The width was 72. Design was 72 inches. Depth, spread footing depth below 60 inches. Design was 60 inches. No water was observed. Test bit number 3, from 0 to 42 inches, we had lean clay, hand penetrometer 3.5 TSF, pretty strong soils at the bottom of the spread footing. The thickness was 18 inches that matched the design of 18 inches. The width was 70 inches. The design was 72 inches. The depth was 57 inches. Design was 60 inches. And there was no water in there. Test bit number 4 for the spread footings from 0 to 48 inches was lean clay. Water was not encountered. And it was 18 inches thick. Design was 18 inches. The width was 80 inches. Design was 48 inches. Depth below grade was 51. Design was 60 inches. And no water was encountered. For the grade beams here, from 0 to 36 inches was sandy clay. The grade beam below the slab was 36 inches. Design was 36 inches. Grade beam width was 14 inches. Design was 14 inches. Grade beam test bit number 6 was 38 inches. Depth below grade is supposed to have been 36 inches. And grade beam width was 12 inches, supposed to be 14 inches. So no water there. Test bit number 7 From 0 to 36 inches was sandy clay, lean clay, and no water. Grade beam depth below grade was 36 inches. Design was 36-inch. Width was 14 inches. Design was 14 inches. No water was encountered. And last one, test pit number 8, from 0 to 42 inches was lean clay. And the grade beam was 34 inches. Design was 36 inches. Width was 14 inches. And of course, design was 14 inches. No water. We checked out some of the bolts around the building, the anchor bolts, to see if those anchor bolts are doing okay or not. Picked up 10 locations. And we did a torque test on them to see what kind of torque we get on these bolts. The torque wrench right there. These are some of the conditions of the bolts. No washer, and one nut and one washer was missed. One of the nuts were missing. Everything was loose, 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 more loose stuff. One nut was missing. Washer was missing. So these are the conditions that we got. Washer missing. Washer was missing. One nut was missing. Everything was loose. Yeah, loose. Washer was missing. Again, washer was missing. And you can see here it's like a bolt insufficient thick length of bolting here. See in here, no washer. We summarized these 10 locations, and every one of them failed in the torque test. The torque was supposed to be 132 foot-pounds, and they all were below 132 foot-pounds for the torque. So all of them failed. And we looked at condition of all the bolts in the building for the anchor bolts, and here's a just summary of them. It says no nuts here, no nuts. Washers were missing. A lot of them didn't have nuts. Washers were missing. One washer was missed. I mean, really in poor conditions, all the anchor bolts were. Laboratory tests, we did classification tests, soil string tests, proctor tests, measured concrete thickness, concrete compressive strengths, and we did petrographic analysis of the concrete pores. This is a soil stratigraphy underneath the building. In the interior building, we had concrete. Below that fill, that was lean clay fill. Below that, we had clayey sand in here, boring B1, sandy clay B2, clayey sand, clay. Below that, we had fat clay. Some areas we had fat clay. Outside, we had lean clay, and then below that, we had sand. Lean clay, sand, and now had some fat clay outside. So we had a kind of a variable soil conditions at the project site. So if you look at it in summary, 0 to 0.62 feet, we had concrete slab. Below that, we had fill, clay sand, 0 to 2 feet, 0.54 to 2 feet, or we had lean clay. Below that, we had lean clay in some borings, 0 to 25 feet. We had some areas 2 to 9 feet. We had clayey sand. Some areas we had fat clay from 14 to 15 feet. And then we had silty sand from 18 to 24 feet. Soil properties, in terms of properties, most of the soils near the surface were low PI, non-expansive soils. The maximum PI near the surface was 26. Started getting deeper. We had some fat clays with PIs ranging from 32 to 46. The sands were medium dense. The hand penetrometers, some of them near the surface were pretty low, kind of a weak soil near the surface. Some areas were strong. Boring logs, interior borings. We had concrete slab, boring B1, 5.5 inches. Then below that, we had clayey sand. Below that, we had clayey sand. That was fill here. Below that, we had lean clay with a PI of 24. Pretty strong lean clay here. Boring B2, we had concrete about 7 inches. Below that, we had fill, lean clay. Below that, the lean clay all the way down to about 11 feet. Below that, we had fat clay. PI of the lean clay was about 25. Boring B3, we had concrete slab, 5.5 inches thickness. Below that, we had fill. Below that, we had clayey sand. Below that, there's clayey sand again. And then lean clay, then fat clay with a PI of about 46. Boring B4, interior. Inside the building, we had concrete slab about 5.65 inches. But we had lean clay. Below that, we have clayey sand. And then below that, we had fat clay. We checked the compaction of the fill. All the compactions passed. Compaction on the slab of the fill was good. Concrete slab, boring B5. Below that, we had lean clay. Below that, again, we got lean clay. That was fill. Below that, we had clayey sand. Below that, we have lean clay. PI of about 12. We checked the compaction of the fill. All the compaction passed underneath the floor slab. They were compacted more than 95% standard Proctor density. In this case, we're compacted to 196% standard Proctor density. That's B6. We had 5 inch but thickness concrete. Below that, we had lean clay fill with a compaction of 100% and 95. All the compaction passed. Below that, we had lean clay. Below that, we have clayey sand. Below that, we had lean clay with a PI of 11. Exterior borings, we had basically lean clay all the way down to about 12 feet. Below that, we had silty sand with a PI of about 25. Same beat boring B8, mostly lean clay all the way down to about 18 feet. Below that, you had sand, and there was no water. B9, we had lean clay, then fat clay. Then we had lean clay and sand at about 18 feet. And we didn't hit any water. B10, we had lean clay with the PI of 11. That fat clay below that. Below that, we had lean clay with the PI of 16. All the way down to about 23 feet. Below that, we had sand. B11, we had lean clay outside. Then below that, we had fat clay. And below that, we had lean clay with PI of about 35 for the fat clay. And the last boring, boring 12 outside, we had lean clay near the surface with the PI of 13. Fat clay below with the PI of 35, lean clay below that. For potential vertical rise is a measure of how much heave we can expect for soil at a particular site. We calculate the PVR using TxDOT 124E, and we measure the PVR about 1.4 inches with this site, which is not very high. So that's got a little bit of expansive soils, but it's not that bad. Proctor test, we got a sample of the Proctor test from the test pits. We ran a Proctor test on it, and we got a maximum dry density of 115 and 12.5 moisture content. We ran the compaction of the lean clay underneath the floor slab on the fill, and all the compaction underneath the floor slab passed. All the compactions were good. Concrete compression test. We took the cores that we got, like this is C2, C4, and broke them. C6, C7, C8, C9, C10. So the design was 3,500 PSI floor slabs. We broke the concrete cores for the cores we had, and we got 2,000, 1,580, 1,540, 2,000, 2,200, 1,980. So the strings failed. The concrete strength in the floor slab failed. The slab was faulty. Petrographic analysis of the concrete. We got some of these cores. We got a thin section of it, of these cores. We took that thin section and inundated it with blue dye and put it under the microscope. They found a bunch of stuff in here, and it just lots of porous cement. They had retampered concrete, which means that they had added water to the concrete at the job site. And so, and then we had some voids. So we had some problems with it. High water cement ratio. So looking at these various pictures of the petrographic analysis, again, retampered concrete, marked with red. This is the basically here. That means it was added. And the cement, porous sections, yellow. These are porous areas. Again, you can see the porous areas in the yellow. Red is retampered concrete. Weak section of core aggregate dislodged from the aggregate, creating a void. Basically, aggregate cracked. Again, the red areas is retampered concrete, yellow porous concrete. This is a crack. Cracks in the porous areas with the cement paste. Here's another one. Again, got retampered concrete areas. You got, the yellow areas, porous areas. Retampering is the addition of water to the concrete mixing and making the whole enable the fresh concrete to be easily poured, placed, and finished. And you can see the basically aggregate small particles from the left is basically porous paste. And here it shows the sections of the aggregate and porous paste around the particles. These are porous paste, and this is the aggregate. This is a coarse aggregate covered with porous paste. Coarse aggregate. There was a void out there in the mixed. Porous paste. And here you can see the porous paste here. So basically, looking at the petrographic analysis of the concrete, we had inferior aggregate used, and they used retampered concrete. That means they added water to it during the construction. Engineering analysis, review of the aerial photographs, review of topographic map, macro elevations, field compaction evaluation, presence of perch water, soil moisture profile, liquidity index, uplift capacity of the spread footings, review of the rainfall data, ground penetrating radar, evaluation of floor slab thickness, evaluation of concrete floor slab strengths, petrographic evaluation of the concrete samples, recommendations on floor slab based on forklift loading, concrete parking lot design based on traffic loading and bolt testing. Aerial photos, if you look at this thing here in 1944, there was nothing out there. We just kind of just land and a few trees out there. Here's 1989. There was a house here. There was a bunch of trees here. In 2004, there was a house. Somebody was living here. Bunch of trees here. 2008, somebody was living here, bunch of trees here. 2014, they removed the house that was just with the land. 2020, they start building the building in 2023. Metal building going in here. 2024. Topographic map shows this flat as a pancake. The area is pretty flat. Elevations. When we did the elevations, we compared it to the F.PTI, Post Engineering Institute Guide for Performance of the Slab on Grade Foundations. There's some definitions here. Definitions of deformation is a change of the shape of a foundation after original foundation construction. Deflection is maximum deviation from a straight line between 2 points. Deflection ratio is deflection divided by horizontal distance over which the deflection occurs. And if the slab is moving like this is the correct deflection. This is not the correct deflection. You don't measure from here to here. You got to measure from this to this. Kind of defining what tilt is and slope. TRCC, Texas Residential Construction Commission, and ASCE, they said your slab can have as much as 1% slope, or 6 inches for a 50-foot slab wide. Tilt is planar rotation, measure the length over the length or width of the foundation. So tilt is y over x. And the slope is a differential elevation between any 2 points divided by a horizontal between them. So we use the F.PA, Foundation Performance Association, allowable criteria for foundation movement, and also F.PTI. The allowable usually is about L over 360. Maximum tilt is 1%. So that's corresponds to 1 inch and 30 feet deflection. So we got 2 sections here of the elevations in here to see what the contours, see what the elevations are. So this is your slab elevations. Changing is the horizontal distance. And we checked for deflections at any point. And we got L over 1, 1607, L over 24, 26. All these things are smaller than L over 360. So the deflections pass. Tilt was 0.4%. So it passed. This is the other section we took. That's the section looking at the slab elevations. The deflections all pass and tilt passes. So in general, section AA, the differential movement was 2 inches, and it passes. In the BB, the deflection was 1.8 inches. It passes. AA, we got L over 1607 average, and allowable deflection is L over 360.
Can you click your camera on? Because you're frozen.
Oh,
I can still hear you, but you're frozen.
camera on and off. Okay. So looking at L over section BB is L over 2054, which is really small and a lot smaller than L over 360. So both deflection and allowable tilt passes. So we don't have excessive flexure in the floor slabs. Compaction evaluation. We ran the compaction test, and we check all the densities of the fill under the floor slabs, and they all passed 95% standard Proctor density. So fill compaction was not an issue at this slab. Perch water table. There was no perch water table water trapped under the floor slab areas. All of our excavations were dry and there was no water coming in. Soil moisture profile. Looking at the moisture profile, this is the interior boring B1, 15 feet deep. Moisture was pretty dry. This is the basically wet moisture condition and dry moisture conditions. And Our moisture was drier than that. So the soils were kind of dry out there in boring B1. Boring B2, our moisture was pretty dry compared to one textile 124E moisture conditions. Boring B3, moistures were kind of average, but still close to dry. Boring B4, moistures were relatively dry. So borings inside the building were usually relatively dry, although this point B5 this looks a little wet. B5 was wet in the top 5 feet. And boring B6 was kind of wet, the top 4 feet. But below that, it was dry. Outside borings, B7, it was wet near the surface and then dry below it. Boring B8 was kind of dry all the way down. Boring B9 was dry pretty much all the way down. B10 was average to but moist near the top 6 feet. Below that was dry. Boring B11 was average in the top 5 feet, and then below started becoming dry. Boring 12 was kind of wet, and then top 10 feet and below that becomes dry. Liquidity index. I want to know how wet or soil your whole profile is for your soil inside and outside the building. For the exterior building, of course, liquidity index is the moisture content minus plastic limit over liquid limit over minus plastic limit. Liquidity index indicates how far your natural moisture content has progressed between the plastic limit and liquid limit. And we looked at it in here is pretty much half the borings inside were dry, half of them were wet. And looking at the outside, most of the borings were kind of dry on the liquidity index. Uplift capacity of the spread footings. The way you calculate the uplift capacity on these spread footings that they're using, of course, you got weight of the footings plus weight on the structure, weight of the soil on the spread footings. And that's QT. Uplift resistance is WF plus WS. And you need a factor of safety of 1.5. So in this case, we had basically a maximum negative reaction to be resisted with the existing spread footings of almost 30 kips. When we went out there through calculations for a 7x7, the biggest spread footings, we calculated a spread footing uplift capacity of about 23.6 kips, which means that during major hurricane loading, the spread footings can come out of the ground. Okay, so the uplift capacity was not good on this project. So we recommended adding helical piles to the spread footings, anchoring time in there with the anchor bolts, and so that the spread footing is not going to come out of the ground during the heavy wind loading conditions. Looking at the rainfall data, the building was built in 2023 and 2024. And you're looking at it in 2023, we had 41 inches of rain. In 2024, we had almost 60 inches. So on average rainfall in Houston is about 50 inches. So 23, when they started, was not that much rain. And then 24, we had a lot of rain. So basically in 2022, 23, and 24, we had 41 inch, 41.75, and 59. So the first 2 years, 22 and 23, we had rain, but not very much compared to the average. But in 23, 24, we had a lot of rain. That means it was built when there, kind of a lot of raining season and stuff. GPR, we looked at the GPR at 10 locations in the floor slab borehole areas to see if there's a steel there. 10 locations to find out presence of the spread footings. In some areas to find out if there's a void and moisture conditions. A large size void was observed near coring C1. So looking at these things here, this is the void that GPR showed that we measured near core C1, about an inch void there underneath the floor slab. That's kind of the void that was there. Look at the B1 area was when they did the GPR. Average concrete thickness was between 5 and 7 inches, which 6 inches the design. Average cover was about 3 inches. Steel spacing was 12 by 12. No void was observed. That's near boring B1. Here, boring B2. Slab thickness is supposed to be 6 inches. Covered rebar 3 inches from earth. 12 inch by 12 inch. Actually, rebar cover is supposed to be 3 inches. And so here we had everything worked. No void was found. Everything was fine. B3, slab thickness 6 inches, 3 inches. Supposed to be cover. Rebar spacing 12 inch by 12 inch. And everything was fine here. Boring B4, again, looking at this 6 inch slab, 2.5 to 4 inch cover, 12 by 12 steel placement. You know, that's the picture. So everything was fine. That's boring B5 area right there. Everything was fine. Well, it says some void was found near the surface zone and moisture saturation found to be high. So in this area had some high moisture areas. That's the area of boring 6. Here we had some void was found near the surface and the moisture separated. So these areas had high moisture. You know, all that, you know, some of that slab didn't have cover on it, the roof, it would rain on top of the slab. And water would penetrate through the control joints into the natural subgrade. Rebar size verification. There was a cut in the slab. We used that to calibrate the GPR machine. We use the GPR to find the locations of the spread footing underneath the columns. And you can see in here, at 10 locations, using GPRs indicates where the spread footings are. You can see that spread footing location. Verification number 8. Void survey. We checked the floor slabs for void. This area here, he had no noticeable saturation, 2 to 3 feet underneath the floor slab. Moisture. That's the high moisture area. Here, no voids was found. This area here, noticeable moisture saturation underneath the floor slabs. This area here, some moisture saturation was found near the surface. This area here, we had some area here. It says noticeable moisture saturation. Also potential void at about 2 feet. This area here, single white anomaly in radar image indicates surface saturation. So this area is here near the surface, the concrete is saturated. Here is another area. You can see not concrete saturated. It was what I would talk about, soil saturated. This area here, it says surface saturated. That's a soil, not concrete. Here again, you can see moisture saturation about 2 to 3 feet in the floor slabs. white anomaly images, surface saturation. These areas are saturated. Again, noticeable anomaly was found in no noticeable. That's this area here had no problem. This area here, it says some small size void-like anomaly was found, 6 to 8 inches deep. So GPR picks up areas of high moisture, high areas of voids, noticeable moisture saturation, 2 to 3 feet. Here's another one here, white areas, because surface saturation. Noticeable moisture saturation, 1 to 3 feet. That's kind of like the soil saturated. Here again, surface saturation. Nothing here. Medium level of saturation was found. Here's a noticeable moisture saturation. This area here, you got radar imaging, it gets high level of moisture saturation. Right over here. This area is a noticeable moisture saturation in the deep 4 to 5 feet. This area, moisture saturation was found locations 1 foot. So look at these things here. You got high areas of moisture saturation. This area here is a kind of a void type thing. So you look at the whole slab again. The area that's kind of like dark blue is the high moisture areas. The red areas are potential void areas underneath the floor slabs. And you get areas of high saturation, some void areas here, high moisture saturation. Slab thickness. The slab thickness range anywhere from 5.5 inches to 7.4 inches. American Concrete Institute says a concrete should not be thinner than 0.25 inches of the design thickness and not thicker than 3/8 of an inch of the design thickness of 6 inches. But here we had that's the thickness is significantly below and above. So the floor slab does not meet ACI 117 tolerance standard for the slab thickness. Strength, we cut the cores out there on the floor slabs, they broke them, and the strengths all failed. If numbers were supposed to be 3,500 psi, numbers were anywhere from 1,500 to 2,000, 2,200. So if you look at ACI 318, it says if you break your cores, average of 3 cores should not be less than 85% design strength and not single one drop below 75%. So in this case, the design strength was 3,500 psi and 0.75 was 25, and 85 average was 85% was 29. And all of our design numbers, all of our breaks fell below this number. So the concrete floor slabs are faulty. Petrographic analysis, we ran the petrographic. It said we had inferior aggregates and water was added to the cement concrete during the construction. So that's why we have low strengths. So recommendations for concrete slab thickness based on the forklift loading. So we have forklift loading on this project. So nobody designed the slab for forklift loading. So we went through PCA method, Portland Cement Association. We have forklift axle load of 13.4 kips, wheel spacing of 78 inches, a number of wheels on each axle, 2, forklift contact area, 40 square inches, the subgrade modulus of 100 PCI, concrete flexible strength of 569, concrete working stress of 335 PSI, slab stress per 1,000 pounds, 13.4. You go through the PCA method, knowing the stress load, axle load, You go to these things here and you go to the effective contact area, and you come back here to the wheel spacing. Then you go this way, it gives you the design thickness of 8 inches. So you should have 8-inch concrete in the floor slabs with the forklifts that we have there, not 6 inches. Concrete parking garage. Astro, we use pavement design for the pavement for the parking areas. You had a lot of 18-wheelers going around on the site, and we ran the numbers using the soil properties that we found on the site. California bearing ratio, resilient modulus, 4,500 psi. Went through Astro pavement design parameters, reliability over standard deviation, load transfer. All these are all Astro stuff. Concrete compressive string of 3,500, subgrade modulus of 80 PCI, and going through the normal graph based on the subgrade. Coming over here, concrete, modulus, and then you go over here, based on the traffic loading and all that. Go to this map in here, match line, design serviceability factor, and then you come over here, reliability and standard deviation, and you go estimated 18-wheel ESAL. You come here together and you have 8. So you should use 8-inch concrete paving in your parking areas, considering 18-wheeler loading we have. So based on traffic loading of 1 million, thickness should be 8 inches of concrete on the subgrade of 8 inches. The subgrade should be compacted to 95% standard Proctor density, lime stabilized, using 5% lime by dry weight. Bolt testing, we ran the bolt testing, none of the torque passed, so all the bolts were faulty. And here's the summary of the bolts that are no bolts, nuts are missing, and washers are missing, and all that stuff. And all the torques failed. Reason for foundation distress: inadequate design, improper construction, poor quality material. The result indicates that the spread footings did not have adequate size and depth to resist uplift loading. So the uplift loading was a problem for the design of the spread footings. Faulty construction can cause problems. Presence of cracks. Review of the concrete core indicates the thicknesses range from 5.5 to 7.4. So thickness of the concrete floor slab was not adequate. In addition to that, the test pits TP1 and TP3, TP4, TP6 all showed inadequate spread footing sizes and depths that didn't meet project specifications. Same with TP8. Poor quality concrete. The results of our concrete test results shows strength ranging from 15 to 2200. Based on ACI, the concrete string failed. So petrographic analysis showed the concrete had retampered, had too much water in it, and also bad aggregates. So in summary, we had inefficient design size of the footings for uplift loading, design defect, inadequate concrete floor slab thickness, construction defect, inappropriately constructed depth and size of the spread footing, construction defect, inappropriately constructed depth and width of the grade beams, construction defect, inadequate compressive strength of the concrete, materials defect, poor quality concrete, materials defect. Repair. 2 options. Based on what we found is A, you go out there and clean the existing floor slabs and put a new 8-inch concrete floor slab on top of it and put it in accordance to ACI 302. You got to dowel a new slab into the existing slab. You can put a new 8-inch slab in there. Option 2 is remove the existing slab, jackhammer the whole thing, and put a new slab 8 inches thick. And also, all the spread footings need to have helical piles to them, add to them to resist uplift loading. These are helical piles, are basically a foundation system that's screwed into the soil, and it's got a helix plates to resist uplift and downward movement. These are helix plates, and of course, this is the bracket that goes under the foundation and bolted in there. So typical, again, these are the helixes. These are bolted to the foundation. Again, you can see the the helixes, the bracket that goes in here, bolts to the foundation, the helix. So they go out there and drill them next to the foundation and connect to the spread footings or grade beams. These are helical piles. You drill them next to the foundation. You can do it in the interior. You have to jackhammer the slab. If you want to do the spread footings inside, you connect it to them. They're small surface area and expansive soils cannot lift them, and they're easy to install inside and outside the buildings. The comments is improper spacing may cause overload of the piers. Piers not installed in the correct angle may lay on the side. They got to be vertical. Not installing the pier in the proper torque, it is not going to carry as much load. Improper anchorage of steel brackets that will result in basically the foundation is not going to resist uplift. You need helical piles if you want to do them. You need some borings. They've got to be at least 40 feet deep. We recommend additional studies. Do a plumbing leak, make sure there's no leak. The structural design, we recommend the structural engineer to review our report, make comments, develop a set of plans and specifications for the repair. Contractor develop a cost estimate, and we monitor the implementation of the repairs. So that's it. We've got a program evaluation. I want you guys to tell me how you thought the program was, and let me know. If you need to reach me, my contact information is de@geotecheng.com. My number is 713-699-4000. Upcoming webinars, we got a bunch of webinars coming up. Just keep tuned to the programs. We'll send you emails about some of the upcoming webinars. If you've got pictures of the projects that are failing and stuff, send it to me. I appreciate it. We use it in our presentations. This program is going to be on YouTube, so if you go to YouTube channel, you're going to see that. We're going to send you PDH hour, about 1.5 hour for this program next week or so. Any questions?